Hey, in the previous video, I have explained how we obtained the F statistic to test a joint hypothesis. So the intuition is the distance standardized by the standard error, but we had to consider the correlation between the multiple coefficients, multiple estimates involved in the hypothesis. But also now the next step is we need to know the distribution of this F statistic. The reason why this F statistic is widely used is because one of the reasons is because its distribution is well known. We know how it behaves. It is like the T statistic is known to have a standard normal distribution as long as the sample size is large. So also the F statistic it has a well-known distribution as long as the sample size is large enough. So we are going to I'm going to introduce the distribution that is associated with the F statistic. And for brevity of the explanation, I am going to consider, as you see here, I'm going to consider the correlation between those two parameter estimates is 0. So we may generalize the theory for general correlation, but it will be more complicated. So let me explain in the special case where all the parameter estimates are independent with each other. And then, so before doing that, let's think about this setup. So let's start from the standard normal distribution. Suppose that Z is a random variable that follows a standard normal distribution. So it is a standard normal distribution, mean 0, variance 1, and then often we are interested in its squared. Its square, Z squared, follows a chi-square distribution. So this the letter that looks like X is a Greek letter called chi. So chi-squared distribution with subscript 1. The subscript it can be different depending on the degrees of freedom of the random variable. So in this case, this is the starting point. We have a standard normal distribution. If you square that, we get chi-square distribution. So the reason why chi-square has a name square is because it is originated from the square of a standard normal distribution. And then, now suppose that there are k different chi-square distribution. And like, hey, this is typo. There are k random variables, and each of them is a chi-square distribution, and all of them are independent with each other. Then the sum of k independent chi-square distributions follows the another chi-square distribution with a different parameter k. So because you added k different chi-square distribution, now you have a chi-square distribution with the degrees of freedom equal to k. So here the degrees of freedom was 1. There is only one variable moving around, but in this case k different variables are added, so there are k dimensions in this distribution. So k degrees of freedom in this distribution. So that's why the subscript is k now. Then combining these two results, you can simply say that suppose that there are k independent standard normal distribution, then square each of them and add them. Sum of squared standard normal distributions follows a chi-square distribution, right? So it's like it's exactly a combination of these two results, definitions. So this is what we are going to use in our analysis. And here k is the parameter of chi-square distribution. Like mean and variance are parameters for the normal distribution. K is the parameter for chi-square distribution. And it is called the degrees of freedom. So you have heard about the degrees of freedom when we learned sum of squared residuals or sum of squared total sum of squares and things like that. So the same degrees of freedom, it is closely related to that notion. And this is how it is distributed. First, it is always positive because it is based on square of something. So the normal distribution can take any number from negative infinity to the positive infinity. But once you square that, obviously it will be always positive. So the starting point is 0, always positive. And when you have 1 degrees 1, k equals to 1, it is dropping quickly. And as you increase the degrees of freedom, it becomes more flat. So 1 is dropping like this, and 2 is more flat. And as you can see, if k equals to 9, then it becomes much more flat. And of course, the mean increases as k increases because you are adding more variables. If you think about this, as you add more variables, k increases, and of course, the mean will increase. So in that sense, the distribution becomes more flatter, and the mean also center increases to the as k increases. So this is the shape. It's a well-known distribution. Then how do we use it? What's the relationship between F statistic and chi-square distribution? So as before, like suppose that the hypothesis is about beta 1 and beta 2. So the joint hypothesis, and assume that, so you can calculate t statistic for this guy and this guy, and then we assume that the t statistics are independent, or the estimates are independent between beta 1 and beta 2. So this is just for intuitive explanation, and we are just considering special case to simplify our argument. So if you assume that, then we learned the F statistic was this form, or is defined in this way: 1/2 and sum of squared t statistics, right? The sum of squared t statistics is divided by the number of parameters. That is the F statistic. And remember, if the sample size is large enough, the t statistic is approximately a standard normal distribution. So T1 is a standard normal distribution. T2 is another independent standard normal distribution. So therefore, the sum of squared standard normal distributions is a chi-square distribution. In this case, the degrees of freedom is 2 because only 2 standard normals are squared and added. Therefore, the F statistic has another additional term 1/2. So considering this, except for this part, we have chi-square here. But as a result, because of 1/2 multiplied, so we say F statistic follows chi-square with degree of freedom 2 multiplied by 1/2. So 1/2 is a little bit redundant, I think, but that's the convention. And so when you have more than 2 coefficients involved in the hypothesis, so suppose that now we are going to generalize the number of coefficients to q. Say there are q number of coefficients from beta 1 through beta q. And also you can calculate the t statistic for each of the coefficient. So t1, t2 up to tq. And we are going to assume that all are independent. Then the F statistic takes this form. So exactly same as before, sum of squared t statistics divided by number of t statistics. So it's a kind of average squared t statistics. Then and as we like in the same way, you can argue that T1 is approximately standard normal distribution, T2 is another independent standard normal distribution, and TQ is another standard normal distribution. So therefore, squared sum of squares becomes a chi-square distribution with the degrees of freedom equal to q. Now it is q, right? So we are considering q coefficients at the same time, and because of this redundantly multiplied 1 over q, we have to say that the F statistic follows 1 over q times chi-square q. So that is our like brief explanation of what we are doing. So then, the chi-square is easily computed by Stata or any computer program. Like Excel also has built-in function for chi-square. So we can calculate the critical value, the cutoff value from the chi-square distribution. So simply speaking, depending on the number of parameters, number of coefficients involved in the hypothesis, you have to choose the minimum value of F statistic that you need to reject, at which you need to reject the null hypothesis. So for example, when q equals to 1, this is a single hypothesis. You only have one coefficient. Then the critical value is simply 1.96 squared. Remember, 1.96 was the threshold for t statistic. Now we are squaring them because everything is squared. So the critical value becomes square of the same threshold. But when q increases, the value changes, and at the same time the value diminishes because the denominator q becomes larger, so the threshold cutoff becomes smaller. So you don't need to memorize that. You don't need to memorize them. It is automatically calculated. And in Stata, automatically calculates the p-value and of course the F statistic. So you can make the decision based on the computation result. So, and however, regression command, the default result, does not have this specific test results. So you have to specify which coefficient you are interested in. So if you are interested in 2 coefficients, you have to write another command, and then Stata will take care of the computation. So like, let's think about this. First, let's look at this. You are regress test score on student to teacher ratio and expenditure per student and percentage of English learners. And this is robust standard error option. So if you put this command, then you get this much result. So this is the default result from Stata. And here you get standard errors and coefficients, but the problem here is you don't have the correlation coefficient. So you cannot calculate the F statistic. Remember, F statistic actually involves correlation coefficient. I explained as if the correlation coefficient is 0 because that is easy to explain. But in general, you need to think non-zero correlation coefficient. So without knowing that, you cannot calculate F statistic from the default result. So the result has t statistic and like 9 confidence intervals, but does not have F statistic. Now you need to specify the test, what you are going to test. So this is the additional command. By the way, you have to put this command right below the regression command. So once the regression is conducted, then in the memory, the regression result is saved. So the regression result is on the memory. So you can add more commands like after the regression command. But if you use a different regression, for example, then the test will be based on a different results or may not work. So the test command should follow, must be entered when the regression result is in the memory. So anyhow, here the rule is simple. Test these two coefficients, student to teacher ratio and expenditure per student. So we considered three regressors: student to teacher ratio, expenditure per student, and percentage of English learners. But we are not interested in the third one. So we are interested in only the first two coefficients. So then simply you type test and these two coefficients. Then automatically it shows that it is testing these two hypotheses. Student to teacher ratio coefficient is 0 and expenditure per student coefficient equals to 0. And then F statistic is given by 5.43. And probability, this is p-value. So p-value computes so this is the p-value computed by data, and it is 0.4%. If the p-value is smaller than your significance level, you are going to reject the null hypothesis. So in this case, you need to reject the null hypothesis, which is clear given the small p-value or the large F statistic. So F statistic is 5.4, but remember the threshold was 3. So greater than 3 rejects the null hypothesis, so it is rejected. And one more thing. So the formula for the F statistic must assume homoscedasticity. So it's based on homoscedasticity, and then in this example, because you are using robust option, so the test is automatically calculating robustness, heteroscedasticity, robust F statistic. So the formula is now different. This is obtained from a different formula based on heteroscedasticity, robust F statistic. But I think this is not widely used. So more commonly used is the simpler formula we introduced here. But as I said, this is not the formula when you have heteroscedasticity and when you use the robust standard error option. So it becomes a long video. See you later.